Welcome surfers, it is Joel and this is a Coding Sounds Lesson 6. Before the lesson, if you aren't subscribed to the channel yet, press that button. It is a good way to support all this hard work. In the previous lesson, we did something pretty brutal. We wrote directly in our code the gain. As you can see here, we hard-coded the value in our plugin processor. This means that if a user wants to change, for example, the gain, the volume, they'd have to recompile the entire plugin, and this is not the best idea in the world. Today we fix all of that with the system that Juice provides to us for managing parameters professionally. The system is named Audio Processor Value 3 State, which everyone abbreviates as APVTS. Before we write any code, I want you to understand why APVTS exists. Think about what happens when the user of your plugin simply turns a noob. First of all, the GUI thread detects the mouse movement, the mouse drag, and calculates a new value. After this, that value must reach the audio thread, but without blocking it. This is very important. After this, the DAW needs to know that something has changed and need tools to save and to restore a specific session and a specific set of parameters. Now, if you try to implement all of this manually, it's a nightmare. APVTS does all of this for you, and it's a simple Juice class that wraps a value tree, flexible hierarchical data structure. Every parameter in the APVTS is identified by a string, a unique string. So let's open our project and create a new file. This file is called parameter eds.h because it's an header. Okay. We need to declare the name of all parameters. This file will define every parameters that our synthesizer will use for its entire lifetime. So we are declaring more parameters than we need right now, because we try to do a structure that should be stable in the time. You define it now, and for the rest of the project you can simply use these strings, these IDs. So, in the namespace parameters IDs, we simply started to declare all the name of parameters. The first of all is the gain. So, inline. Okay. Now we need a lot of other parameters, so you can simply copy and paste all this section in your source code. The oscillator section, the filter section, the envelope section, and the filter envelope section. And this is all we need. In in use, the APVTS constructor require a layout of parameters that is called parameter layout. Parameter layout is an object that describe every parameter we use inside the plugin. To create this object, we'll write a standalone function that builds this layout for us. The easiest way to do this at the moment is put this function inside the plugin processor source code, and at the start of the file, so before the constructor. The function is a static function that return parameter layout. Okay, now it's time to make a pause because there is a lot of things in here. Let's break down the important concept of this code. The first parameter of the add function is the parameter ID, is a composite value because we have the string of the ID that is declared inside our parameter ID header, and we have the version number. If in a future release you rename a parameter or change its range, you must increment this version, and use can detect that a saved session was made with, for example, an older version of this parameter and handle this kind of mismatch. After this, another very important thing to say is what is the normalizable range and the skew factor. The constructor of normalizable range define different parameters. This is the minimum value of the range, this is the maximum value of the range, and this is the step of the movement. We can also declare a fourth argument, the skew. And the skew parameter is a parameter that define how the DAO use this range of values. The skew is very important for frequency parameters. The default skew is 1. This means that the mapping is linear. But for example, if you set a skew of 0.25, the midpoint of the nub 0.5 is a normalized space, maps a value much closer to the minimum. For example, for the cutoff filter, a skew is very important because without the skew, the first 10% of the movement of the nub would sweep from 20 to 2000 Hz. Most of the audible bass and mid-ranges. And for the remaining 19% of the nub, you cover a range you barely perceive. Is not very useful. If you use the 0.25 skew, you can distribute the perceived pitch change across the nub full rotation. So this making the control feel musical, feel better for the person that play your instrument. Now, this is the parameter of this reasoning. Now, we need to integrate the APVTS into the processor class. So, inside the processor header, we need to do some changes. The first change is to add APTV as a public parameter. So, juice now we can remove this gain at the moment because we don't use it in this new version of the plugin. And now we can add the master gain parameter, that is the main parameter that we use. Okay, we can put here. We need an atomic float. And this is a pointer, because APVTS owns the memory of this parameter. You simply have a pointer to the memory that is directly managed by Juice. Okay, perfect. Another very important thing is that APVTS is declared in the public section. And there is a specific reason for this, because the editor, the graphic user interface, will need to access this parameter to attach, for example, a slider, another component, and also the DAW need to access this parameter through the graphic user interface. Now, let's update also the constructor of the plugin processor. This is our constructor. Now, we can add our constructed list of parameters in this plugin processor. So, the first thing to do is to add this parameter here. Okay. And now we can put our master gain parameters inside the constructor, and we can relate it to the master gain inside our APVTS layout. Now we can replace the hard-coded gain value with the real value, the DAW connected parameter. And we can do this inside our gain processing and inside our prepare to play function. Inside the prepare to play function, we simply convert the new kind of parameter. So we can delete this. And we can add the new parameter. Okay, and inside the process block we change something in the gain processing. So we need, we can delete many things. And now we can re-add the parameter value in decibel and convert this value to a linear gain. Now, in the module 4 we build a full preset system, but let's wire the basic state management for parameters. So the ADO can already recall our parameters correctly and can save and restore a specific session. To do this, we need to replace two functions: the set state information and the get state information. We can start with the get. We can serialize all the parameters of APVTS in a single binary blob that can be saved by the DAW. In the set state information, we need to do the opposite thing. So we need to deserialize and this state, this binary blob, and restore it in current APVTS values. Okay, 6 line. With this simple 6th line of code, your plugin survive a full save and reload cycle in any standard DAW. Now, at the moment we are not built the final graphic user interface for this plugin. That's the module 5, but currently we need a way to test that our parameters work in some way. And just provide a kind of shortcut to show in a built-in editor all the parameters with contained in your APVTS. It's ugly. It is not an elegant and beautiful solution, but it's very important for testing. And you can simply replace the editor in the create editor function. So here we can simply return a generic audio processing editor. Okay, and now we can build and remove all the reference to the old editor, to the old interface. Let's run this code and say what is the aspect of our plugin. This is all for this lesson, so see you in the next one and keep your thinking cap on.